Here we are. Good evening, everyone. Thank you for joining us this evening for another exciting edition of Bridge Builders Academy. My name is Japira Keys, and I am here on behalf of the Department of Family and Community Engagement. We are thrilled to be with you tonight to have this discussion and to learn all about the impact of number sense and building mathematical fluency for the success of all of our learners. Tonight, we will have Mr. Billy Rothert with us from Mathnasium as our presenter. We ask that you please mute your microphones and feel free to use the chat to answer or ask rather any questions. Without further ado, our presenter, Mr. Billy Rothert.
Thank you very much, Japira, for that introduction. As mentioned, my name is Billy Rothert. I am the Center Director of Mathnasium of Tuckahoe, which is in right kind of that Richmond and Henrico border area. And today we're going to be talking about, well, specifically math in K through 8, but the subject that we're going to be talking about is number sense, number fluency, a brief history of math curriculum in the United States and how that's affecting the greater Richmond area because Virginia is rather unique when it comes to math curriculum. So let me go ahead and present here, share my screen. All right. So the presentation today is my number senses are tingling. This is going to be a discussion of what number sense is, what numerical fluency is, why these things are important, how they're different from your traditional computational skills, and some of the history behind it. First, I would do just a quick poll. This can be really simple. Just anybody in the chat could raise their hand or give an emoticon. Have you ever heard someone say, I'm not a math person? I'm just not really a math kind of person. I'm sure many people have heard that before. But my question is, when did that become okay? When did it become okay for someone to say, I'm not a math person? Consider this, for example. How strange would it sound if someone said to you in a professional setting, maybe an interview or a conference, I'm just really not a literacy kind of person. I don't really do that whole, written language thing. I leave that for the other folks that are more into like the books and the writing. I'm not really a literacy person. That would be absurd. And you would look at that person as if they were as if they're from another planet. Like, what you mean you can't read? That sounds as absurd to me when someone says I'm not a math person because numbers are so integral to how we operate on a day-to-day situation. Now, contrary to popular belief, being a math person is something that can be taught. It's not just some innate gift. It's not, a divine blessing on some and not to others. It is a skill that can be trained and learned. But what exactly are we training for? The simple answer is Algebra 1, but the more complicated answer is society at large. Today, we're just going to be focusing on school for now. So everything we learn from grade K through 8, that math is aiming at preparing a student for Algebra 1. And in the same way, you could say that everything taught in the high school courses, Algebra 1, Algebra 2, geometry, trigonometry, these are all aiming towards calculus as a content area. Now, why should we care about training that skill? I mean, it seems like people were doing just fine without number sense and numerical fluency before. Well, the truth is, that's true. Your parents probably got along in grade school without the use of number sense and numerical fluency. And it's possible that many of you in the audience did as well. However, that won't work today. That will not be sufficient for your children. Math has definitely changed in schools, and it's a bit of a rabbit hole to even discuss how that happened. The biggest reason is that today there's no centralized mathematics curriculum that everyone learns in our nation. Our government bodies have very little say over what is taught in schools, and the overwhelming majority of funding and curriculum design happens at the state and local levels. So this means that the United States functions almost like 50 individual countries, all teaching in their own way. Now, there's certainly plenty of overlap. It's not like, an entirely different system. 2 plus 2 is still 4 no matter what state you live in. But it's enough of a difference to cause some serious problems. Now, how did this all begin? Math as a subject area is ancient, goes back to ancient Chinese and Greek and Roman civilizations, but we don't have to go back that far to tell this story. We only need to go back about as far as the Enlightenment area, maybe in the 17 and late 1800s. This era of thinking gave us a scientific method. Great scholars like, for example, Isaac Newton and Rene Descartes, they influenced the academic landscape for math and science, but really they built the foundational bedrock upon which all math and science is built today. Then, from the late 1800s up through the maybe 1950s, one of the most popular models of mathematical learning was an educational philosophy called constructivism, which was popularized by academics like John Dewey, Maria Montessori, and Jean Piaget. This all changed in the mid to late 50s, and the catalyst event in our society that triggered it was actually the space race and the Sputnik crisis. Quite frankly, because the United States didn't get to space first, we made the decision to revamp how math was taught in K through 8 schools. It led to what is referred to as new math. It was created based on ideas like set theory and Boolean logic and very abstract math concepts, and it was a complete and utter failure. And that's what many people are thinking of when they hear about new math being taught. Well, fortunately, new math died and, and stayed thoroughly dead by the end of the 70s, but there wasn't really a good system to replace it. Once it faded away, one of the most prominent educational philosophies that came about was something called the Summerhill model, though it wasn't as prevalent as new math was. It was proposed by a scholar named Alexander Sutherland Neill, but this had its own problems. And the 70s, as many of you might know, was a decade in which our country was sort of against the idea of like structure and authority. So the Summerhill model was an ultra progressivist educational movement based on similar principles where students could effectively choose what they wanted to learn and when. And I'm sure you can guess how that worked. It wasn't very successful either. So there was like a 20-year gap where we were bouncing from new math to a very, very unstructured math. And it wasn't until the 80s that our nation tried to regather itself under a unified math curriculum. That was the dawning of one of the more successful systems called everyday math. This was initiated in the early 80s, but new versions of everyday math have been released in every decade since. It's sort of a back to basics approach, focusing on really functional and like practical math skills. It has its pros and cons, but for a while it was the only thing that was even remotely close to a national standard. Currently, we have in many parts of the United States the Common Core State Standards Initiative, and it's been working pretty well in some of the areas where it's been adopted. Although I think it's largely misunderstood. People don't quite understand that how it's to be implemented. I think in a large part it gets a bad rap due to a stumble upon its implementation. But the Common Core State Standards was one of the um, one of the most recent and best attempts to unify our nation under a single math curriculum. However, because our government can't force one particular state to join or not, it was still left up to state by state. And guess what? Virginia did not adopt it. We have never adopted the Common Core math curriculum. So again, we're sort of left in this tricky position where we don't really have a good standardization of what to teach our students or how to teach it. In fact, from where I'm sitting right now, kind of in the west end of Richmond, I could throw a stone anywhere a mile or two from here and hit one of 6 or 7 different math curriculums. We've got people that are teaching everyday math in some of the independent schools, students that are learning Singapore math in some of the independent schools, homeschool students are practicing anywhere from Saxon math, Abeka math, various different models. Henrico and Richmond are slightly different. It's fascinating for me as a math geek, but very, very difficult for parents and teachers and students to operate in an environment like this academically. So how is this resolved? What's the key to having students, parents, and teachers navigate the mathematical landscape so that students can be comfortable and confident that they have the right kind of skills developed? The best way to get started with this is actually to use a comparison using language. And I realized that I've been forgetting to, or my slides haven't been flipping, so I'm going to skip ahead a little bit past some pictures and onto this one. Okay. So fortunately, the previous slides weren't really informative, but this one is something that I want people to see. So this is just a general breakdown of um, how much communication is verbal versus nonverbal. But many of you might have heard about this, that in a lot of ways, the words that we actually say are only responsible for about 7% of the communication of our ideas to people. Other things like the tone of our voice, the inflection of our words, account for much more of the language, as well as things like body language, our physical presence, the gestures that we make with our hands. These are what actually deliver the ideas of our communication to the people that are listening to us. And it's pretty easy to see how this is a an intuitive thought, right? This isn't like a crazy idea. People can communicate lots of different things to each other without the use of any kind of words. And I would say that being a really strong math student has a similar kind of breakdown where there's more than one skill involved. I would say for mathematics, it looks something kind of like this. I would say that in this pie chart, the smallest slice of the pie is a student's actual computational ability. True, it's important. There needs to be some skill and practice dedicated to simple addition, subtraction, multiplication, and division fluency, but it's not the primary focus. If someone is going to become a math person, they need number sense and they need numerical fluency. Okay, so what is number sense and what is numerical fluency? Number sense is the intuition that allows you to navigate a math problem. I think navigation is the best word to use to describe this because number sense establishes your orientation within a given problem and helps you understand the direction you need to travel in order to solve it. Number sense asks the question, what kind of math problem is this? What are they ultimately asking me to do here? And I think that number sense is comprised of four primary components. The first pillar of number sense is interval counting. Interval counting is being able to count from any number to any number by any interval, forwards or backwards. This topic permeates all levels of math, from pre-K up through calculus and beyond. So every time we count 1, 2, 3 in grades, K or 1 or 2, or if we do patterns in grades 3 or 4 or 5, or if we plot the slope of a line in algebra, or if we do things like sums, series, and sequences in calculus, that's all counting principles. And so as you can see, there is this line of continuity where there can be counting type questions at all areas of math. The next major pillar of number sense is wholes and parts. Wholes and parts is when we break things down, perform some combination of operations, and then we put them back together again. We do wholes and parts theory every time we do addition that involves carrying, whenever we do subtraction that involves borrowing. Those are some of the K through 5 skills. We do wholes and parts every time we do fractional parts in maybe late elementary or middle school. If we're factoring polynomials in algebra, that's wholes and parts as well. You can also graph functions piecewise in pre-calculus and calculus. These are, again, common themes that spread through all the K through 12 areas of mathematics. Third, we have proportional reasoning. So generally speaking, proportional reasoning refers to the fact that numbers can have a relationship that rely on multiplication and scale, not just addition and subtraction. It's the basis of multiplication. It's how we make equivalent fractions. It's how we reduce fractions. It's basically everything in geometry that involves similarity and congruence. It also relates to things like economics of scope and scale in graduate level business classes. So proportional reasoning, again, follows all the different content areas of math from grades K through 12 can touch on concepts of proportional reasoning. The last major topic in number sense is inverse operations. So inverse operations is the understanding that for pretty much any math operation you can perform, there is a different math operation that will do the opposite, that will undo that operation you've just performed. Addition is the inverse of subtraction. Division is the inverse of multiplication. Square roots are the inverse of exponents. And you've got exponential functions and logarithms and derivatives and integrals. You can see a common theme here. A big part of how number sense operates is knowing what functions to perform to undo and work backwards through some operations. Okay, so when a student sits down and looks at a new math problem, students too often think, okay, I'm learning something new. This is an entirely new piece of information. I'm going to craft a little island and plant this new knowledge right in the middle, and I'll have to build everything from the ground up again because I've never seen anything like this before. That is far from the truth. In fact, all these areas of math connect together. I've already demonstrated how interval counting, wholes and parts, proportional reasoning, and inverse operations have common threads throughout all areas of mathematics from K through 12. And so when a student sits down and this student has great number sense, they have their number sense navigation tools ready, they can say, this question is fundamentally asking me to do a wholes and parts thing. Well, I can draw upon all the background information from all the other times that I've done wholes and parts in my past, and I come to the table with a sense of comfort and confidence, knowing that I've done stuff like this before. And I can approach this question using the knowledge from previous content areas that are going to help me. All right. That's the general breakdown of number sense, but next is the numerical fluency. So like I mentioned, we need to have two things here that will create sort of that fully robust math student. Okay, so numerical fluency is a different kind of skill. It's more technical. Number sense, if number sense is the practice of navigation, numerical fluency are the navigator's tools. Numerical fluency fills your toolbox full of the right skills in order to approach a math problem from start to end. It's how you would facilitate that journey from the start of the math problem to the end once you know where you are and where you're going using number sense. Numerical fluency helps you actually traverse that distance. All right, so numerical fluency, specifically I'm talking about the K through 5 realm here, and even more specifically, I'm kind of getting into like I really kind of a K through 2 focus here, but there exists a version of numerical fluency for grades 3, 4, and 5, grades 6, 7, and 8. There is even a version of numerical fluency for students in high school, but for the purposes of our discussion, I'll do a demonstration here of what grades K through 2 might look like, because it'll be pretty easy for everybody to understand. I've got 5 different skills here up on the screen, and these, generally speaking, make up the first half of what numerical fluency has to offer. The first skill is addition facts, where the sum is less than 10. An example of that is 5 plus 2. The two numbers that you're adding are less than 10, and the answer is less than 10. We're not crossing over that 10 boundary. The next area of numerical fluency is decomposing single-digit numbers. This would be an example like the number 7 breaks apart into 4 and what? All right, this gets into that wholes and parts theory. The third area of numerical fluency is 10 plus a single-digit number. So taking the base number of 10 and adding a one-digit number to it to create those teens numbers. The next area is double facts, where you're adding numbers that are the same up through 12 plus 12. Again, an example here could be 7 plus 7. And finally, we have the complements of 10. So what numbers go together to make 10? For example, 6 goes with blank to make 10. That's the first 5 areas of numerical fluency, and they are among the most fundamental math concepts that a student can learn. You'd be surprised at how many students that I work with that are in grades 4, 5, 6, and beyond, and they really don't have these basic skills mastered. There's 5 other areas of numerical fluency that I'll go into next. The first of this next tier of numerical fluency concepts is addition facts with sums greater than 10. An example of this could be 7 plus 8. See, the key difference here, while you would realize that they're both still single-digit numbers, they cross over the boundary of 10. It's actually surprisingly hard for students to grapple with, especially at younger ages. Crossing over the boundary of 10 presents a kind of cognitive barrier, and many students aren't able to grapple with it. Well, a student with great numerical fluency might recognize that they know that 7 plus 7 is 14, so 7 plus 8 should be one bigger, as opposed to students who will maybe have to finger count or make tally marks or dashes or tap their toes or do any other kind of inefficient or inelegant way of solving 7 plus 8. The next area of numerical fluency is subtraction facts with the minuend less than 10. Again, we're not flirting with that boundary of 10 in this content area. We're doing single digit subtraction where the answer is going to be between 1 and 9. The next area, topic 8 here, is missing addends. A really challenging cognitive jump for students is to reorder the problem and say 8 plus blank makes 13. Students can grapple with 8 plus 5 in a number of different ways, but saying 8 plus blank makes 13, that's quite a bit harder. There's a lot of different ways that students can approach this question, but one of the ways that I like to teach my students is to recognize that they would need 2 to match up with the 8 to make a 10, and then they would need 3 more to make 13. And that's actually appealing to the previous to two of the previous numerical fluency skills, complements of 10, so what goes with 8 to make 10, and then 10 plus a one-digit number. So as you can see, the foundations here in numerical fluency build upon themselves, just like the rest of math does. So this system is designed in that way to foster students building a wealth of understanding behind them. The last two areas here involve subtraction. We've got subtraction facts, minuends over 10. So again, we're now going to cross that 10 boundary where you have a number bigger than 10, subtracting to a number smaller than 10. And then missing subtrahends, which is again that blank in the middle where you have a subtraction question where we're trying to cross that boundary of 10 and find the missing number in between. So this is a pretty detailed breakdown of numerical fluency. It's much more technical than like the general overview of what number sense is. But whenever I hear a person say, I'm not really a math person, math isn't for me, I don't like math as a subject, it's probably because they're missing one of these two key skills, number sense and numerical fluency. So going back to my initial chart here, the student that is comfortable and confident and able to approach math without any fear or hesitation, they have both number sense and numerical fluency under their belt. And if your student, either your child or a student that you're working with in the classroom, has a fear or apprehension about doing math, I think you should examine one of these two areas and say, is my student not very fluent with their number facts? Consider their grade and age to see maybe they are not fluent in multiplication or fractions. If they're in the grades K through 5, you should look at their addition and subtraction facts like I just went through and see, are they really up to speed on those key skills? And if they're missing number sense, then they might not realize that, for example, a proportions question, maybe let's say we're doing like a ratio question, is built on the same fundamental understanding as multiplication and fractions. So those are the two areas that I think that students should focus on to become a robust, mathematically gifted student. Okay, so kind of wrapping things up here, and then we'll go, if we have any people in the audience, to some Q&A. Why did I go into such detail on these really fundamental things? Well, it's because number sense and numerical fluency aren't part of an established math curriculum. You can do number sense and numerical fluency with any student, regardless of what curriculum that they're using, regardless of their age, regardless of their previous experience with math. You can start building these skills through the development of these two areas of math, and it'll increase your students' comfort, it'll increase your students' confidence, it will increase their elegance and efficiency with solving questions so that they are less likely to make careless or computational mistakes. and they have more reliable ways to solve math problems. So if I were to give one piece of advice or one skill to teachers and parents in the Richmond or Henrico area, it would be to look at number sense and numerical fluency as the ultimate goals for your curriculum and instruction. You should be aiming at these skills when designing your curriculum, designing your lesson plans, differentiating your lesson plans, and doing assessments, because this is what makes someone truly into a math person. And thank you so much. I will open up for any questions if anybody has any. But otherwise, I will turn it back over to you all.